Hey everyone, welcome to the AI show. I am Cassie Breviu. I am here filling in for Seth today. He's taking some much deserved vacation time. And today we have some really cool content for you. We are going to be looking at multi-platform deployment with ONNX Runtime. We're going to be looking at how to deploy a super resolution model and an object detection model on mobile and web. So I also have some special guests that are going to be joining us. So you are not going to want to miss this episode of the AI show. Hey everyone, welcome to the AI show. These are my special guests today, and they are some interns on the ONNX Runtime team that are working on some really cool stuff. So even though they're interns, like, this code is amazing, you guys are going to see some really cool stuff. So why don't you all introduce yourselves? And we'll start with Victor.
Hello everyone, my name is Victor Aikosuji. I'm a computer engineering major at Howard University, all the way from Nigeria, and I'm so excited to be on this show.
Hi, my name is Khalia. I'm from Atlanta, Georgia, majoring in computer science at Spelman College, and thank you, Cassie, for having us on the show.
Hey everyone, I'm David Vasquez. I'm from Queens, New York City, and I'm studying computer science at Rensselaer Polytechnic Institute. I'm really excited to be here.
Great. Well, we are excited to have you here. And Victor, why don't you tell us a little bit about the project that we're going to be looking at today?
All right, I will. So our project is to build a mobile and a web application to perform super resolution on images. And this time we'll be using the ONNX Runtime framework. Now, the reason behind this project is to improve object detection on these images by using a super resolution output. And by doing this, we are also showing how robust and adaptable the ONNX Runtime framework is on different platforms.
So cool. So you are going to start off, right, showing us some really cool React Native stuff. So why don't we get your screen ready to share? And then Khalia and David, we are going to be inviting you back to talk about your parts in a little bit. So we'll see you in a little bit. Victor, can you pull up the code that you have prepared?
All right, I will. Okay.
Thank you.
We already have a repo for our project, and we have the link right there, and we have a few examples where we use the mobile for the super resolution, and we also use the web for the super resolution. And now we're going straight into the code. So
are you able to make that a little bit bigger? Can you scroll in or zoom in a little bit with your browser? It's kind of small. Is everyone else able to see it okay?
Can you see it?
Yeah, I can see that. Can you go back to your code? Yeah. Okay.
Okay. So usual, when we're dealing with machine learning models, we need to accept the input image. We need to pre-process the image to make it ready for our model. And after we've gotten the output from a model, we need to post-process the image and view the image so the user could see our output. So starting from the beginning, from selecting the image, we have our image picker function. And also, just to add, we built this project using React Native, and also we used Expo. Now, just to explain, Expo is a React Native like framework where you could easily build apps that could be deployed on different platforms. So I have it right here.
Yeah, this is cool. I had never actually heard of Expo before you were talking about this. So it's almost like if you do, like, I always think about things in C# because that's where I started. But like if you think about Xamarin and how it allows you to use C# to write mobile applications and deploy to multiple mobile platforms like iOS and Android, Expo does that for React Native, right?
Yes.
That's so cool. Like, I didn't know this existed until y'all showed me this project.
Right. So with Expo, you just need to write one JavaScript project that could run natively on different devices. Now, yeah, back to the code. So all this was written in JavaScript. Yeah.
So it's really cool because we're able to then use this JavaScript to deploy on mobile and web, which we'll see later. And we're able to share code across the different implementations of the models, right?
Right.
Yeah. So cool. Okay.
So now we have our open image picker function. This function is responsible for asking the user for permissions, and once the permission is granted, we're able to launch our library and be able to select an image to be used in our model. Now, our model accepts the pixel data of our image, and so we had a problem in our pre-processing where we needed to get the pixel data of our image. Now, doing that in JavaScript proved to be difficult, but React Native has this really cool feature called native models, where let me pull it up. And this native models, like with native models, you could actually build models and functions in other languages like C Sharp, Swift, Java, C++, and you could be able to reuse those models in your JavaScript code. So
that's cool. So this allows me to write my pre-processing in a different language other than JavaScript, because I have done JavaScript pre-processing for computer vision projects, and it's definitely difficult to do in JavaScript. It's doable, but it's definitely more steps, and some of the other languages that handle data better work better for that data pre-processing, right?
yeah.
So yeah, that's super cool.
All right. So using native models, I was able to write a function called getPixels that's able to get the pixels of an image given the image's URI. So I'll open up the code right here. As you can see, we have this getPixels function which was written in Java, and what it does, it takes the file path of the image and is able to generate a bitmap image from that file path, and then we're able to get the pixels from that image, and then the image is sent back into our JavaScript program. So right here, this is where we get the image, and then we get the pixels from the image. So this is a really cool feature from React Native where we could use these native models. Okay.
Cool.
Now onto the pre-processing. All right. So unlike other models that have to do some processing on the red, green, and blue values of our images, our model actually has to work on the luminance, which is the Y component of our image. So first of all, we have to convert our red, green, blue image into a YCBCR image, and our model is gonna work with this float pixels Y. So that's why we have this right here. We have the red, green, blue values from our pixel, and those values are sent into this utility function right here. So this is a function, and this is where all the conversion takes place. It's just a lot of arithmetic operations that works on the red, green, and blue values in order to get our Y, CB, and CR values, and those values are sent back into our main mobile app. So depending on the mode, you can get your Y, you can get your CB, and you can get your CR. And
So this isn't. Oh, sorry. Go ahead.
Oh, no.
I was just going to say, I think this is an interesting part about super resolution models, because most computer vision deals with RGB, right? If you've done any other computer vision stuff, you know that you generally just have to do RGB. But with super resolution, in order to actually improve the quality of an image, we need the Y channel, and the Y CBCR is actually what HD, like that's the input that HDTV is taken as well. So I think it's interesting when you start thinking about these other types of formats and why they're important for this type of model.
Yeah, exactly. Yeah. So for this model, like you said, it uses just the Y channel of our images. And since it uses only that channel, then we create an ORT tensor array with these dimensions, and this tensor is returned back into our model. So as you can see in our run model function, this is where we do most of the running, where we get the tensor from our pre-processing function, put it into a feeds dictionary, run our model with the feeds inputs, and get our output from the model. Now that we've gotten our outputs, the next step is to post-process the outputs. So
Did you show the load model though? Because there was another cool thing about this because of the type of model you use for ONNX Runtime, right? You had like a specially optimized one.
yes, so before we could run our model, we need to load our model into the specific environment, right? So we have a function for that, which is our load model. So we get the ORT model. So now, as you can see, this model is a Super ResNet 12.ORT, and as you can see, it's an is in ORT format.
And the ORT format is like an optimized ONNX, because like usually when you use ONNX Runtime, you export to an ONNX model, which has some optimizations. But in order to get an even smaller, more optimized model, you were able to convert it to an ORT or ONNX Runtime format in order to get it optimized to actually work on mobile.
Yeah, talking more on that.
Yeah.
Let's go into that. So this is the reason why we use the ORT format. So with the ONNX format, it could still work, but with the ORT model format, we can get a reduced size build, and these builds are really optimized for for mobile applications and for web applications, because this is as you can see, a size constrained environment for that. So ORT format models are the way to go for building applications with mobile and web. Okay, so
Super cool.
Back to the code. And once we've gotten our model, we create an inference session with our model, and then we can run the model. So after we've gotten the tensor from our pre-processing function, we run the model with our inputs and we get an output from our model, and then we post-process our output right here. So now going into the post-processing function. Now this post-process function takes in an array from our model, which is basically the output array from our model. And since we're working with the Y component, to get our output image back, we need to change the YCBCR back to RGB. So we'll be using this function right here, to change the YCBCR back to RGB, and this takes in the Y, it takes in our CB, it takes in our CR, and you're able to get the red, green, blue values back. Now, depending on the platform, there are different ways the pixels are returned. And for the Android part, we have to return the pixels, we have to return the values as one pixel, as one hexadecimal pixel. So we do some binary operations on the pixels, on the values, and get our hexadecimal pixel back and return that pixel. So now we have this integer array which represents all the hexadecimal pixels from our output image. And now that we have our RGB image, now I'm also using a native models function to get the output image source. Now, if we want to display the image, we need the source of the image. So we need to get the image URI given the pixels. So what this get image URI function is responsible for, also written in Java. This is responsible for creating a bitmap image from the pixels that we got, and then creating a temporary file in our platform, whether on the Android, it's going to create a temporary file there and put our image into that temporary file. And once we have that temporary file source, we're going to send the source back into our main JavaScript code. Now that we have this source, we're going to display our output image. So yeah, that's it for the mobile implementation.
That's cool. There's a lot that you did there. Like you kind of went like it's once you have it all done, right? It seems simple when you can explain it, but there were so many things that you did in there that are really hard. Like being able to pre-process the images in non-Python languages. Like Python's really useful for data processing, and so being able to do that in JavaScript is really cool. And I always think like the pre-processing and the post-processing in non-Python languages tends to be the hard part when you start to use and want to operationalize and inference your models in other languages. So this is a really cool way of how you're able to take an image, and we're going to see this work on Android. In fact, maybe I should stop talking. Let's just see it work, right? Let's see this cool demo that you have going.
All right, so we have a demo right here. So basically you upload an image, select the image, and then we process the image. And after a few seconds, we get our outputs right there.
Wow, look at how much more crisp the second image is. Like, look at I feel like the fur, you can see it a lot on.
Yeah.
So that is really cool. And the other cool thing is the model's running all on the device. So this is a local deployment. There's no like call out to an API, like a web API that has your model hosted in the cloud somewhere. It's all happening real time on the device using the hardware of the device itself. And so it's cool that you're able to optimize and then use ONNX Runtime to do that. And so this would be the first step, right? So now we have the first step of we have this image that we want to get a better resolution so that we're able to do object detection on and get better results, right? But you showed the way that we can do it in mobile. We can reuse a lot of this code, right?
Yes.
Okay, so I'm going to add Khalia back. Oh, and she is going to show us the same demo here. There we go. The same, well, not the same demo, but how she's able to take and reuse a lot of this code that they wrote and deploy the same model now in web and do inferencing in the browser, right?
Right.
Cool. Okay, is your screen ready? Oh.
Yep, it's ready.
All right. Oh, and there was one question by Jay here. I just want to throw this up here. He said, love that he's using TypeScript versus Python. Makes me wonder if you can do it in C#. That is a really good question. And I think you could. So you'd have to be able to, like, if you mean the pre-processing part that he was doing in Java, let me bring Victor back here for a second. You said that you were able to use C# in those modules for React, right? Like the module that you used for Java?
It's possible to use C# for that.
Okay, so you could do those different, C# functions that you did in Java. You could use that in React and then still use all the same JavaScript code that you had.
Yeah.
If you wanted to do the whole thing in C#, you could do that as well. And actually, after this, the first part where we're looking at this mobile and web, I'm actually going to show some C# natural language processing with the BERT model doing all of the processing in C#. So we are going to look at that later, but it's going to be natural language processing. But basically, to answer your question, I'm pretty sure you could do everything you just saw in C# as well, if you wanted to. Okay. All right. Bye again, Victor.
Bye.
We'll say bye to you again before we're all done. Okay. All right, Khalia. Let's get your screen shared. Cool. All right, so what are you going to be showing us? You're going to be showing us how to do this in web, right?
Absolutely.
Awesome.
All right, so first let's establish like the difference between like what I have to do for, of course, web and of course what you have to do for mobile. So how we got the data for our pre and post processing is different. So I use Canvas, off-screen Canvas and just Canvas. So I can see right here, I use the Canvas API in order to get the image data, and also use off-screen Canvas. So like, of course, you do not see everything that's going on in the background. All right, so basically getting this, starting here with this KDB variable, we're just basically just making it type off-screen context so it can get the context for, of course, your off-screen canvas. And of course, our load and run model are the same, except of course, it's just the pre and post processing that is different. So let's start with our pre-processing. So first of all, pre-processing, we have to get our data. So in order to get our data, we have to use our off-screen canvas and create one. So here in our draw function, this is where we create our off-screen canvas and draw our image onto the off-screen canvas. And then from that image on the off-screen canvas, we can get our data to go into the pre and post processing. This first little paragraph right here, this basically just gets the data for the 224 by 224 image that goes into the super resolution model. And this second a few lines right here gets the data for the 672 by 672, the second scaled image when it runs through the model afterwards. So after we've drawn those images onto the canvas and gotten the data, we can now go through our pre-processing function. So of course, like Victor has said, we have to put our data onto the Y channel because of course that's what Super Resolution has to use in order for it to run. So how this data is, so versus mobile, we don't have to go through, of course, going to back and forth between APIs because the data is already in RGB format. Like all we have to do is just kind of put the data, store the data in something and just convert it from RGB into YCBCR. And of course, this is where we do that right here. And of course, I've this already shown you guys. This is the function to go from, of course, an RGB format to YCBCR. And these are the same. Oh, go ahead.
So I was just I think you were gonna say what I was gonna ask. This is the same code, right? That like
this is literally the exact same code, but the only difference, of course, with the second going from YCB to CR to RGB, like it's just simply using the R red, green, and blue values. You don't have to like convert it back to a hexadecimal pixel.
Got it. Cool.
All right, so the same thing is happening for the CB and CR array, except we're not using the image data from the 224 by 224 image. Instead, we're using from the 672 by 672 image that the model outputs. So from the 672 by 672 image, we just get our CB and CR array that we'll use later in our post-processing. But for our pre-processing specifically, we just need our Y channel. All right.
Awesome.
So after the pre-processing is done, we go into our post-processing. So of course we have our output array. In our output array, we have to go, of course, we've got to get our pixels from YCBCR back to RGB. So of course we just have the Y channel. So we have to put the CBCR back to the Y channel in order for it to convert to RGB. So like I said before, for the web part, all we really have to do is just get the red, green, and blue value. Since it's already in the red, green, and blue value, we don't have to turn it back into a hexadecimal pixel. So it's a bit easier on that side of things.
Okay.
So once we kind of convert it back to YCBCR, not YCBCR. Once we convert it back to RGB, we can go ahead and draw our image from our off-screen canvas onto our canvas that the user can see. So of course, right here, we're just creating our canvas that is in the return statement. And of course, we're just creating the context for that canvas. And then after the code established that, of course, the context and the off-screen canvas are not null, then we can go ahead and put this image data from that we cleared earlier. Because we clear everything that every time the user picks an image, we clear because we don't want a whole bunch of background images just be going on the off-screen canvas. So we cleared the images before. And here we're just putting that image data back on the off-screen canvas, save it so we can get that image from the off-screen canvas and put it on the canvas that the user can see. And of course, we save that image. And after that, of course, the image is just returned and displayed to the user.
That's cool. So there's so much stuff that you're able to reuse between these two. So like if you had a solution, like if somebody had a solution that they wanted to be able to run on multiple devices, there's a lot of like write once, run everywhere here, right? And build once, run everywhere type usability, which is really cool and super useful. Okay.
Go ahead.
Oh, go ahead. What were you going to say?
I was going to say I have a demo, but.
That's what I was going to ask for. just like with the shared function, I'm like. That's
of course. So just like the on mobile, this is the welcome screen. Just click next. So you can pick a photo. We're going to use the same one that Victor used for mobile. Run our model. And then, of course, it outputs a Super Resolution image.
So cool. And this is all happening on the device in the browser. There's cool things about running the model on the browser too, or on the device. Like it's cheaper because you don't have to pay for, hardware to do inferencing. So that's one cool thing.
Right.
Another cool thing about it is the data all stays on the device. So from like a privacy perspective, you don't want to be sending your data across. If you're running your model on mobile or on your device, you're able to do that as well. So there's like lots of different kind of features that allow you to that are good about being able to do on-device inferencing. Some of the things to think about is if you don't want your model downloaded onto people's devices, maybe you don't want to do on-device inferencing. That's like one where I've heard where people don't want that because they don't want to share their model out. And and then also the size constraints of it. So you guys were able to use an ORT model that allowed you to optimize it enough to work on these different devices, but sometimes models aren't able to do that. I'm curious, do you know if the model was quantized at all, or if all you had to do was literally like export to ONNX and then export to ORT? Do you know?
I wouldn't say all I had to do is Victor did most of that, but I think from what he said, that is true. But get back on Victor with that one.
Hey, Victor.
Yeah, hello.
So you're saying, so did you export to ONNX and then create it or then convert to ORT, or how does that part work?
All right, so the model was already built in PyTorch, and then we converted the PyTorch model back into the ONNX model, and from the ONNX model we converted to an ORT format. So it wasn't really quantized, yeah, but it's a small model. As you can see, the outputs, we get the outputs really quick. So yeah, it's a really small model. So
cool. Okay. Thanks. Anything else part of the super resolution that you all want to share before we jump into the object detection side of this project?
Nope, unless anyone has any questions, and that's everything that we have to show you guys today.
All right. Does anybody have any questions on that first part? I'm keeping an eye on the chat. See, we have some familiar names joining us today. That's awesome. Good to see you all. All right, well then we will bring back David and say goodbye to Khalia and Victor for a little while. And so David, what part of the project did you work on?
So I mostly focus on the object detection part of the project. So as we said before, the overall story is we basically just want to take an image and then ultimately use object detection on that. So basically just detect objects in the image. But in order to do that, we use the super resolution model to increase the resolution of the photo. So the overall object detection would be more accurate and just better overall. So that's the main purpose of our project. But let me just hop into the nitty gritty of things. So I got the model. It's a convolutional neural network model. And it's in the ONNX, or it's in the ORT documentation. So if you guys want to go over that, you could. And the model originally was a TensorFlow model, but I had to convert it to an ONNX model and then format that into ORT format. So that's kind of just more background of the model that I use in my project.
So for this, you're using an open source model that was already prepared, and you were able to then just export it into ONNX format ORT and then reuse that, right?
Yep.
So did it have to be fine-tuned at all, or it was able to just use kind of the out-of-the-box object detection model?
It was mostly out of the box, I would say. Yeah.
Awesome.
Yep. And just like a little more information about the model. This is an app called Netron. I'm sure some of you are familiar. It basically just allows you to analyze and break down a model. And here just like some more information on the model itself. It's ONNX model, just some more data behind it. So yeah, I guess we could just hop right into the nitty gritty of things.
Tool you're using, Netron, if people aren't familiar with it, it's a super useful tool to kind of get some information on the different model, like inputs, outputs, and then also taking a look at kind of the weights through each layers and such. So I'm glad you showed that. It's such a useful tool to understand when you're grabbing open source models and you need to know more about what it's expecting and the formats and such. It's such a useful thing. Yeah,
definitely. It was really useful when understanding the inputs and the outputs and exactly how to operate the model. So it's definitely very useful. So yeah, let's just hop into the code of things. All right. So I guess most of this, the first part is mostly the same as before, as Victor showed before, is just loading and running the model, just basically just reading the model is mostly the same. But where the most of the differences come into play is pre-processing and post-processing the images. Because of the nature of the model, I'll just bring you back here. The inputs and outputs are different. The inputs, it inputs a UN8 type data type model, while Victor's model is a float type model. So breaking that down is slightly different. But the vast, where it was mostly different was the outputs. As you can see, there's 4 different outputs, and it's better explained over here, actually. Here, exactly. So there's 4 outputs. The first output being the location. Basically, it returns an array of 4 values between 0 and 1, and basically just gives the location of where the box is for the object detection when the model. So like right here, when like something's actually detected, the 4 points, the 4 corners, so that returns that value. The second is the classes. Basically, just returns the label assigned to a key. I'll just show you guys. So basically here, like it returns a value, a number, and it's assigned to what the object is detection. In our case, in our model. So if there's a person, it'll return 1 for being a person. Third is a score. It's a value between 0 and 1. It's just returning basically how accurate the model believes it's detecting. So if it sees a person but it's not so sure, it'll be like 0.7, so it's like 70% sure. And lastly, it's the number of things that are actually detected. So if there's like a photo with like a bunch of different varying items, it'll detect a bunch of that. So it just returns how many things are actually detected. So that's kind of like where the main difference in our code lies when it comes to pre and post processing. It's just basically understanding what's inputted and what's outputted. So let me just hop into the code of that.
Right, and then you're actually doing RGB because with object detection, that's more of like the with a normal convolution and computer vision type of format.
Exactly. Yeah. So if you guys remember, Victor mentioned that to break down the images to be inputted to the model, they had to use something called a Y channel. But for my model, I kept the RGB values as they were, and I just made that into a single array. Essentially, that's here in this pre-processing function you can see here. And the reason why I need to keep it consistent, the RGB values, is for the model to actually detect the objects that are in it. So it needs to stay consistent to that. And some more differences here when it comes to post-processing is basically just outputting the bounding boxes. So that's kind of like one of the issues that we had, because so once you run the model, it returns the data, the 4 outputs, as I said before. Yeah, it returns this, but just basically making the app usable. So basically just displaying the locations, the 4 values. That's kind of a hiccup that we ran into. So that's kind of like, essentially that's like most of this code. It's basically just drawing the pixels. So when I hop into it for a second, it's basically just detecting where the location is in each detection box, and basically just analyzing each pixel and then converting each pixel to a color red. So in our image and our process, our method, we thought it was easier to just actually manipulate each individual pixel and change it to the color red. So it actually forms a box as opposed to like using an overlay, which we thought was a fairly usable method for us. So yeah, it's kind of, most of this is just logic behind just drawing boxes and pixel manipulation. So yeah, I guess I can hop right into a demo.
It's working.
Yeah, so the first demo I have is, let me just zoom in. The first video that I have is the model running on a photo pre-super resolution. So if we just use the same dog photo as before, and you run the model, as you can see, like right here, like it draws the box, and then it says like it's a dog, and it's like 70% sure that it's a dog. But if we do that after running the super resolution model, just give it a moment. Yeah, so using the image after super resolution, you can see that the box is slightly smaller and it's also more accurate. It's like more certain that it's the object that's detected. So yeah, I don't know if you guys can see, but like the box is like slightly. Yeah, it's more.
That's super cool.
Yeah, so just like that's kind of like the whole premise of a project, just making the object detection overall just more accurate. So yeah, that's about it.
Wow, that was really, really cool to see how we're able to take the original image, and you could actually see, you could see it. I wish when we did the demo, I would really wanted to be like they did in like Opens, and be like enhance image, and then like
yeah.
But that's so cool. So we're able to take that, and there's so many real world use cases for this. Like the other thing that's cool about that is if you're making a decision on like a threshold of the like accuracy that you get back from an image classification, you're able to get more confident results after improving the pixels. And like there's a lot of different when you're working with computer vision, there's a lot of different issues that you run into with it, and resolution is one of them. So that seems like such like a common sense thing to add in to a lot of machine learning pipelines now.
Yeah, definitely. We just really wanted to show off like the portability and the usability, like the practical use of ORC, and just use that like in a real world scenario of, I guess, like how you said that enhance, like how that's kind of used. So yeah, we just want to use like a real world scenario and just show the capabilities of ORC, basically.
Yeah, and then yours was also running on device, right?
Yep, also on device.
Yeah, so it was all running on device through an optimized model. They're all open source models, right, that people could go use?
Oh yeah, it's open source, so you can access it if you would like. Yep.
Right, cool. And then the code's also open source, right?
Yep.
Yep, and I actually see Microsoft Developer posted some of Victor's code there, so you can all go take a look at it yourself. And then also, if you wanted to do, like Jay mentioned about doing it in C#, you could take that and augment it for your solution.
Yeah.
Which is what I'm going to show you guys a little bit about what I did in a different one after this. So anything else you all want to share with everyone? Or any other questions, I should say, if anybody has any questions about their project, now would be the time to ask. Okay, people are being quiet. Okay. Well, thank you so much for hanging out with me today and sharing this really cool project that you've been working on.
Yep, definitely.
Thank you for having us.
Yeah.
It's glad to be here. Love being here. Just like expressing everything to everybody on the live.
That's so cool. You guys are so brilliant. I can't wait till like you're gonna be my boss someday, and I can be like, remember me and remember the AI show.
All right. Thank you so much. Thank you so much for doing this. All right.
Wow, like such impressive people, such cool things that they're working on. Okay, so what we're going to be doing now, I think is cool. That theirs might have been cooler than it was, probably cooler than mine. But what we're going to be doing now is looking at a natural language processing model. And so we're going to be looking at a BERT model, and let me get that ready to show here. Let's see. I love that bumper. I still needed more time though, so give me 1 second while I share my screen. Snap. 1 second. Should have played that music that Seth had going, or that Seth has, that I am using. All right, cool. Now you can see my screen and we can look at what we're going to be working on. And Jay said, very impressive. It was. Their project is super impressive, and so many like real world scenarios that it could be used on. So for the next one, I think most people are probably familiar with BERT, which is a natural language processing model. And this one is bidirectional one, and there's many different versions of it now. So they made this base model, and then they were able to kind of optimize it for different scenarios. And so what I wanted to be able to do was take this, and there's many kind of examples within Python on how to use these, but I wanted to do all my processing in C# because I love C#. And I wanted to be able to inference in C#. And so ONNX Runtime has a C# package that we're able to do that with, but there wasn't really any samples that I found. So this is actually a project that I've been working on this week. I just got it working like yesterday, legitimately. So I'm going to kind of bring you through my journey that I went on of building this out. So the first thing I did was I was like, well, which BERT model do I want to use? And I started with this BERT base uncased, which is like you have a masked a word in a sentence, and then it shows what the predicted words would be. So I kind of started playing with that one. And then I found this other example, which was on our ONNX Runtime docs for question answering. And I decided to go with this one. So I'm able to actually use the Python Transformers API to get the model with Python. So that's what I started with. I'm like, I'm going to use Hugging Face, and I'm going to use their API to get my model. and get it exported into the ONNX format and do all that in Python. And then once I have that model, I want to see how I can actually then use it in C#. So I actually copied and pasted this code from this doc, which I will paste into the chat for you all here. There we go. And from here, I went to my VS Code and I created a notebook. So I don't, if you don't know, you can use Jupyter Notebooks right in VS Code, and I'm even using my Anaconda environment all within VS Code. So to create a new one, you just go to your command palette and you create a new Jupyter Notebook. So I went in here and I'm like, okay, so let's get this code, let's get this model. So I ran this code, and basically, if you're familiar with the Hugging Face transformers or library, they make it really easy to just grab different pre-trained models, and they have a really cool, on their site, you can go find all kinds of models and also information on how to use them and information about the models themselves. So I went and I ran this, right, which I've already ran, but I can run it again here. Downloaded my model, which is the BERT for question answering. And then changing the model to evaluation mode, creating a dummy input, because we're going to need this in order to export it into the ONNX format. So this is the format or the shape of what the model expects for the input. And then here is where we're actually just using PyTorch. So PyTorch has an ONNX export built into it, which if you've used PyTorch and ONNX, you're probably familiar with this. If you haven't, it makes it really simple to take a PyTorch model and turn it into an ONNX format. And from there, what we're going to do is we're going to give it the model. We're going to give it the different inputs here. So these are the different tokens, the input IDs, which I'll go into this a little bit more in a little bit. The attention mask and the token type ID. So these are the 3 inputs that the model expects. I'm going to give it the model path, the offset version. So there's different versions based on the different operators that are used to actually create the neural network. And different versions support different configurations. So that's what that does. We're going to give it our input names and our output names. So what we're expecting for the label to come back once we do our inference. And then we're going to use dynamic axes. And so what this actually allows us to do is to have a dynamic shape input, because we will be working with different length sentences. So we need to add those dynamic axes so we can use dynamic shapes in our model. So from there, we get that model exported, which you see here. And then we are going to take a look at some of the pre-processing here. So again, this is all directly from our doc here that I sent in the chat as well. Now this one's using AML. I'm just doing things locally, but if you wanted to leverage cloud compute, or if you needed to have more resources than you have locally, you could do that. So this is just the same code that I have here. So we're going to do our pre-processing, which is where we're going to actually tokenize the text. And this one, we're actually sending in a question and a context to the question. So I love that the question in the docs is a Dolly Parton question, because I love Dolly Parton. I mean, who doesn't love Dolly Parton? She's just amazing and talented. But the question and context, I'll go down here really quick to show you that what was there was, what is Dolly Parton's middle name? And then the context has the answer, and then it's able to answer that question. Now, I added the second one. Oops, and I have a misspelling. Where's Bob Dylan from? Because he's from Duluth, Minnesota, which a lot of people don't know that he's from Minnesota. So I added that one in, which was also a singer-songwriter, right? So that's what the input is expecting for this particular model, is that question answer. The tokenizer is already provided through the transformers here as well. So this is where it gets difficult, right? Because in C#, we also need to be able to do this pre-processing. We need to be able to pre-process our model and tokenize it within C#. So how do we do that? There is this open source project that is amazing. Let me throw this in the chat. And so this BERT tokenizer is what we're able to use in order to tokenize the BERT model in C# because we can't obviously use the transformers package and the tokenizer and just download that from the Hugging Face Hub, because that's in Python and we want to be able to do this in C#. So we are actually going to leverage this open source project here in order to do our tokenization. And if you look, they have some nice sample code here, so you can see, you can get your input, your BERT input that you need. There's different tokenizers available. I think it even said, so these are the different ones that are available. Now, if you have like an optimized one, like we're using one that's based on BERT base uncased, but it was optimized after that, we are still able to use this same tokenizer because the tokens have all the same IDs because it's based on that base model tokens. So this, I think, should probably support most BERT models that you find out there. You just need to know which was the base model that it was fine-tuned from in order to use it. So yeah, and then when it comes to installing these packages in C#, you do it just like you would do any other. You can do it through the CLI, or you can go to your manage NuGet packages. And you can see we've already installed that. So these are the different packages that we'll need for our C#. We need our ONNX Runtime managed. We need ONNX Runtime. And then the tokenizer package. Okay. So that part of solving it was actually pretty easy because somebody else already did the work for us. So yay, open source, right? Yeah, and that basically what that provides, or what that returns, is this encoded input. And if I scroll down here, you can see our input IDs, or the encoded input. Run this again. So you can see these are the different tokens. And if you remember when David was showing us for the object detection model, how it had the different IDs and the different words that are attached, that's tokenization. You are turning words into numbers. I always think that's like the simple way to talk it. Like when you think about natural language processing, it can be really intimidating at first, but like really we're just turning words into numbers, and then we're running some formulas on it, and that's the simple way to put it. But anyway, so you can see here's our tokenization. All right. So for post-processing, we'll go over that later. We're gonna, for the init, we were just grabbing that model from the transformers and our tokenizer and getting that ready, and then also using ONNX Runtime to create our inference session. And it's optional. I don't think you actually have to say which execution provider you want, but if you want to specify, if you want to use like CPU or GPU, you can do that when you set up your inference session. And then to actually run the model, we're sending in our inputs, we're pre-processing, getting back the tokens. So the tokens are actually like each individual word, and then also the encoded values. And then from there, we're able to just get the send in the model input. Session.run, this is running our inference, getting our output, and then displaying the results. So you could see it was correct. Our question was, where is he from? If I comment this one out, we can run the Dolly Parton one. And her middle name is Rebecca. So this was the source code that I started with, and I wanted to understand how to actually implement this in C#. So if I go to my C# code, well, let's take a look here. Any questions so far? Anybody? Has anybody played with BERT models before, or done anything cool with them they want to share? Because you can do, there's so many different versions of it. So we're looking at like a Q&A one. There's also, sentiment analysis, sentence completion, all kinds of things. I'm sure I'm missing others. Okay. So the first thing I did was create a console app. So I'm just running this as a console app, and that's usually what I do when I'm, playing around with different C# implementations. But the cool thing is that you could have this in your C# project, and you could have it all part of your main code. If you were having, maybe you have a data science department, and when they're done creating their models, they just go, here you go, and then you have to figure out how to operationalize that in your actual production application. This would be a cool way to do it if you're a C# shop and you're doing a lot of C# programming and applications. So here you can see the question. And when we run this, I'm just writing out the sentence. And this is the tokenizer that we're going to be using. So as I mentioned, you saw how there was like the different tokenizers that you can use in order to, based on which one the model was based on. And so this one was based on BERT large. And if we go look at the source, let me see if I can find the source for this one. I thought we could actually see the vocabularies. If we go into the text file here, this a little bigger. So you can see just like before, we can see the text file. It keeps going. It's just still loading because it's a very long text file. Maybe I zoomed too much. Let's reset that for a second. There we go. So you can see that all of the word encoding and the IDs that they're associated with, just like with the computer vision label file. And so we have these large vocabularies that are then turned into the objects that we're able to use to tokenize. So you can see that. Cool. So that's how this part works. High level how that part works. And then we get our tokenizer, and then we're going to get the actual tokens of the sentence. So let me run this actually so we can take a look as we go. So if you take a look, there's 37 tokens, and you can see the token and the index of that token. Right, so that's our step one, and we're going to need these when it comes to our post-processing to figure out which token is the answer. Then we are going to call encode. We're sending in the length, so we needed to know how many tokens we have, so we're sending in the sentence and then how many tokens there are. And if you take a look at the encoded input, now we can see the ID, the attention mask, and the token type ID. Right. And then from here, we're using that same object that they had in their documentation to put it into a BERT input object and separate those out, because like if you see right now, it's a tuple of 3 objects, and we want to add it into this object. So now we can look and we can see we have our 3 arrays that we are going to have to turn into tensors, and then ONNX, named ONNX value objects in order to process our inferencing. Any questions on that so far? Y'all are quiet today. I saw you in the beginning. I saw everyone saying hello. Got Ivana. Okay. Oh, and I actually saw the question earlier. I meant to say something. Jay had asked about Blazor and C#, and that's on my list of things to try. I think that looks, where it is. Here it is. So maybe I have to put that on the docket for maybe the next time that I take over the AI show and take a look at how we could use that, because I think it's really cool. And if you don't know what Blazor is, it allows you to run C# on the client in the browser using WebAssembly. So I think it should work, but I've never tried using ONNX in Blazor. And I've had that question before. And so I think like once I start getting that, I'm like, okay, time to play with that. Just like I did with this. This was a question that we had, and I'm like, this is a cool thing to build. At least I think it is. Okay, so we have our model here, which I've just added over into our project. We're going to load that. And then we need to convert these to tensors. So I created this helper method that's going to take our array, and it's going to turn it into a tensor in order to process that with our model. So this is the shape of our tensor. So when this dense tensor is an object that comes from ONNX Runtime package. When it comes to so obviously when you're doing stuff in Python has all of the data types you need and everything, and it has all the bells and whistles for doing machine learning. So when you start to do inferencing in other languages and doing those pre-processing like we saw with the example earlier, and now you need these different objects that aren't necessarily available. So ONNX Runtime has this tensor object available within the ONNX Runtime package, which is super useful. So then we're just going to create that. This is the shape that our model is expecting, because we can batch it if we need. So just like with the other ones when they were changing the images, reshaping them to 224 by 224, that one had a static size input that we had to reshape it to. This one has dynamic for the sentence, but it does need to know how many batches of sentences we're sending. So this is just going to process that and turn each one of our arrays here, arrays of long, into a tensor object. Another breakpoint here. Okay. So then the ONNX Runtime inference session is expecting a list of these named ONNX value objects. And so we're going to create the tensor itself, and then create a list of those and add it into this, since this is what it would. Even if you have one value, you still need to create your list of named ONNX values, because that's the type that the inference session is expecting. So the other thing that we're adding here is these labels. So these are the labels that, if you remember from when we inferenced our model, if I go back over here, remember, these are the labels that it's expecting for our model, which you define when you convert your model to ONNX. So we need to set those up here to make sure that we get the input correct and that it knows what is what. And we can take a look here, and now we can see that we have an array of an array of an array. So many arrays. I know. So you can see this is the shape that the model is expecting. So that's great. So then we just have to run inference. Or I'm sorry, create our sentence, or create our session. Here we're creating our inference session from the model path. This one is where we're actually running the inference values. Much faster. Okay, great. So we have these two results, right? So we had the start logits and the end logits, and that's exactly what we expect. So again, if you go back here, you can see, where did it go? Oh yeah, here, where our output names are. Oh, the other thing I was going to show you that I think is really cool. So when I first started using this tokenizer and I was playing around with different models and stuff, I was like, well, are my tokens correct? So if I go to my encoded IDs, you can actually see them here and compare them. Now, I think I have a different sentence. So, and I also spelled where wrong. I wonder if it handles the misspellings, like if it fixes them or how it does that. I actually don't know. So let's run this one quick. And so then we can see the token values. No, where is it? Here it is, encoded. You can see the encoded values. Okay. So we have the results now. And so the results are returned in the inference result of the, like, how confident, right? And then it's in the order of the index of the labels. So in order to get our actual predicted answer, we need to first get the max value, and then we need to get the index of the max value, both from the starting and end, because it could have multiple tokens that it wants to return. So it gives us the start and the end of the indexes from the tokens that we sent in that it predicts are the answer based on the highest inference result. If that makes sense. So that's what this one is doing here. So it's saying index 24 to 26 are the predicted values. So if you were to look here and go to 24 to 26, right? And Okay. Now here we are going to, there's a separator, like kind of a token that goes at the beginning and end. And so we're skipping that first index that's added when we tokenize. And then we are going to just take the values for that range of the predicted tokens. And we can see these are the predicted tokens, which is the correct answer, Duluth, Minnesota. And then we're going to write those out. So if you take a look at the console here, it's kind of small. You can see the answer or the question and the answer. So does anybody have any questions they think we should ask this BERT model? Anyone? So it's funny too, like when I do these projects, this one took a while to figure out, and you'll even see like a lot of my debugging happening here. So one of the things that I was looking at when I was talking about, looking at, are my tokens the right thing? Is my shape the right thing? Am I getting the same result from Python and getting the right shape of the tensor? So a lot of times when I'm doing this, like I think the process of how to take some Python inference code and actually turn that into another language inferencing code is really useful, because when you go and you start grabbing different open source models that you want to use and operationalize, which is like, there's so many great ones out there. I think a lot of times it's easier to just go find one and you fine tune it with these great large language models that are out there, but then you need to figure out how to inference it. And so you can do that by actually just checking out the source code of how they did it in Python and then translating it into C# or whatever language you want to do. Okay, so that was the question answering model, but there are other models. So I'm thinking that we should play around a little bit and find maybe another model and then see if we can go through the process of converting the Python inference code into C#. So let's see. This one was the Q&A one, which we already did here. There was another one that I was looking at up here. What's this one? I think this is text classification. Okay, so we could look at text classification. And again, you can see, so this is the base uncased. So it is the same tokenizer that we're already using. It's distilled, so it's a smaller version. And I think we already, let's import this. I think I have everything here. Let's see. Cool. And then so we have the auto model for sequence classification from pre-trained, grabbing this model. All right, setting the path based on the model name. Did I stop this? Okay, I did stop that. And then if we go down here, so same process like from the other one, where then we're setting our inputs, our input values. And again, this one has dynamic axes because it is a variable sentence length. And then the inputs on this one is a little bit different. We have input IDs and the attention mask. So I want to look at the source for this one, which I think I have. Let's see. In here, let me grab the source for text classification. Okay. So this example came from our ONNX Inference examples. And this one has, so actually, if you ever are looking for examples, this is a really good place to go. There are tons and tons of examples, and they also add new ones when new things come out. Like I think the new .NET MAUI support. Oh, that's actually probably interesting because we were talking about C#, right? So the new version of ONNX Runtime, the one that just came out, supports .NET 6 and MAUI. So, and they just published an example on how to use that. So that's exciting. And the inference examples are where we usually host those. So in this inference example, we're looking at a text classification one, which I believe was this one. Oh, and look, Expo and React Native. That's what this example is using. And this actually is an example that is not, I don't think this one's quite available yet. It's still being worked on, but we can still look at the export here. Okay. Yeah, cool. Let me make sure we have the code also to pre-process on this one, because we're going to need that if we're going to convert it into C#. See, augment model. What does this one do? So this is using ONNX extensions, which is something we're working on now. Let's see. So nope, that's the different export. Nope, that's what I just looked at. Where is the... No, this one might not have it. Let me see if I can find pre-processing code for this model. So let's search. Now this one's from Hugging Face, so I would think that the Hugging Face site might have the pre-processing example. So text classification, tokenizer, let's see, PyTorch. Well, we might have to try to figure it out without the help. But that's okay. We have Netron, so we can probably figure it out without the sample code, even though, you know, I love some sample code to use. So let's see. Let's look back at here. Okay. And okay, so this is the model, and I need to actually copy this over. Yes, I know you can't display that file. That's not what I wanted. I'm going to copy this over to our C# project. And I'm going to rename this to something less useful. I call it BERT. Best. The best BERT. Let's call it best BERT. It's super not informative. But okay, I'll add text classification just because clear naming is important in programming. We need to know what things are. All right, let me copy this and put it into our C# project. All right. Go back here. We're going to have to change that because this is not question answering. Let's add a line. And we're going to copy this one out because we're going to use a different model this time. All right, let's go back here and let's take a look at, so when we exported this model, the shape, okay, so it still has the batches, but it only has a tension mask. So actually that would be useful. It doesn't have the token IDs. Now I think this should be, so this said it was DistillBERT based on, I guess we're gonna find out if this one works with this tokenizer. I think it will because it's just a distilled version of BERT based on case. So I believe the tokens IDs should be the same, but we will find out. Okay. So we have our dynamic link, and this one we only have the output logits. Okay, and actually, you know what? I think I might just start a new project rather than augmenting this one, because this one is good the way it is for this. And I think we're going to have a lot of changes. So we'll reuse some stuff from here, but I think we actually want to start a new project. Create a new project. There we go. And I'm just going to do a console app. Call this best BERT classification. Oops. Type. There we go. And I think I want to keep it in the same directory. Is there going to be any? Yeah. That's fine. We're going to be using .NET 6. And if you haven't used .NET 6, .NET 6 kind of brought everything together. There was kind of .NET Standard and .NET Core and all these different versions of .NET there for a little while now. .NET 6 brought everything together in one, which is nice. And .NET 6 you can run on all platforms, right? Mac, Linux. Okay, so some other things that are new with C#, like, so the first time when I was creating my console app to start the other one, I was like, where's my stuff? Like, what is this? This doesn't look like C#, but you can do this now in C#. It's crazy. So I clicked on this new console template and took a look at what was going on. And you can have this simple, just script it out, which is crazy. But I'm old school and I want my old way of doing it. But you know what? It still supports that. So if you're like me and you want, and you're old and you want to do it the old way, you can still do that. You know, I want like my classes and I want to create my functions and all of that. Okay. But I can see how it'd be super useful to use the new way of doing it too. So I think that's kind of neat that they're doing that they're adding these like flexibility of, you know, like more of a scripting kind of functionality of just running it that way or this way. Okay, so now for my BERT classification, I am going to copy and paste some of what I had. Like, for example, I still want my BERT input. Now we're only going to have 2 of the, oops. That's not where we want to go. Here. Yeah, I know it should be in its own file. Please don't judge me. You know, we're just scripting things out here. We're doing things a little bit weird. It's okay. Okay. Any questions so far? No, no questions. Okay. There we go. That's what I wanted to do. I have 3 screens and somehow I still need another one now that we're doing it this way. Can never have enough screens, right? All right. So you can see we're missing some of our NuGet packages. Again, I'm doing this the old school way. You could do it through the CLI as well. And actually, can I just, oh, I thought there was like, usually it will show like, hey, import package rather than going here. I don't know why that's not showing up. So we want to install this BERT tokenizer package. So as I was saying, like this is that open source package that's available now on NuGet that you can just grab and use. We want to install our ONNX Runtime packages, which I think I could just search ONNX Runtime too. I don't have to put in the full in here. So we want to install that. And we want to install the managed. Okay. Was that all the? Oh, we also want this Microsoft ML data. Why do I not see that one? I think, will this do it for me? No. What are we missing? Well, you know, we don't actually need these attributes right now. This would be like if you were taking JSON and serializing it. I don't think we actually need those, so I'm just going to comment that out. And I'm not sure if we're using this. So because I don't want to figure that out right now, we're going to be lazy and just make it disappear. Okay. So I still want my BERT input. We still are going to have an input sentence for this classification one. We have the attention mask. Oh, that's right. We're not going to be using this one either. So we can grab this. We don't need this anymore. And in a sentence. I don't know what to write here. Anyone have anything better than that? How about something that has I don't know, what do we like? Machine learning? There we go. That might do a little bit better than just I'm a person. Okay. Oh, hey, Jay. Glad you're still here. So you caught up. So I think you know what we're doing, right? We are building out different BERT classification models in C#. So, okay, so we have our BERT input now that we needed that. We added our sentence. And let's see, what do we want to do now? So we need our tokenizer. So you can see the different ones. I think we still want the uncased large tokenizer for this one. We'll see if we have any issues with that. And then we need to get the tokens of the sentence because we need to know for the encoding how many tokens are in it. Let's see. What does it encode? Tokens. Look at that lovely IntelliSense. Thank you. I guess it's IntelliCode because I'm using VS 2022. This is actually an interesting thing about VS 2022. Their IntelliCode, you can actually train on your code base. So it's using a GPT-2 model, which is a large language model that they optimized and actually runs locally. So like we were looking at those other local models, they got a version of that so that the IntelliCode in VS 2022 is actually AI powered and can learn from your code base, which is really cool. And so we are using IntelliCode. I still call it IntelliSense, but it's a little bit more advanced. All right. This was not what I wanted to do yet. Wanted to do, what did I do? Oh, I need to tokenize. I did tokenizer.encode. I need tokenizer. I was so excited talking about the IntelliCode. I was doing the wrong thing. Okay, we want the here tokenize. Yes, that's it. And then we want to send in the sentence so we know the tokens that we have. Again, tokens are just the sentence broken up into words, and then the tokenizer turns those into numbers. Do this, but we're going to have multiple. So when you do a string.join, we need our separator, and a comma. And another. There we go. Cool. Save that. Okay, so we have our tokenizer. We've got our tokens like we needed before. Next, we are going to encode the sentence. And that I'm just going to copy that over because I think it's the same, right? Okay, so now we have our encoded value, which is going to be the same. And then we want to break that out into our BERT input. And now this is not, we're not using this because in this one, we just have IDs and attention mask. So that's all we need there. And we also only have one output here. Okay. Cool. I don't think we need to write that out. Well, just because we're probably going to have to debug some things, we'll do it now so we don't have to add it later. Although we could also just set breakpoints, or we could do both. Why not? But for this one, I just want the BERT input IDs and why are you upset? Oh, I forgot a comma. There we go. Let me check and see if anybody has any questions. Nope, no questions yet. Okay, we'll keep going. All right, so we still need to do the model path. Our model path is, oh, we need to copy our model over here, don't we? That would be important. We need the model. And this is the best BERT text classification. And didn't I save that here? No, I saved that in, I think, NLP C#, right? Yes, there it is. And I'm going to go in here and we're just going to paste it here. Now, we're just doing little console apps and putting the model in with the application. You might have a model registry or maybe a blob storage where you then have code where you go and grab your most recent model. Maybe you're doing overnight training and you have up-to-date models every day or every week. So there's definitely like better ways to do this part for like a production application. But since we're just kind of in the experiment phase of seeing what we can get to work with C# and BERT, we're just going to paste the model right in. And then I'm going to copy the full path, and I'm just going to update my string literal to my new path. All right. And then from there, we're going to create our inference session. I could type this out, but I also can copy paste, and we know that that is just so much faster. Okay, so now we have the model. We've set up our encoding. We have our tokenizer. Then we are going to still run our inference. Oh, wait, what do we need to do? We missed some steps here. Yes, we did. Okay. We need to create our tensors. So we need to convert to a tensor. All right. And we don't need this one. And we need to bring in our helper function here. Okay. So cool. Now this one has the same shape. It has the, I believe, because it was the token, like if we look at our random here. So we had our batch and our input IDs, the attention mask. And if you look here, that is the same. We just don't have the token type IDs. So that's the only difference for the shape. So our shape should be right the way that we've created it here. Now, if you had an input that was a different shape, you'd want to change that in your create tensor section here. Okay. So we've created that. We've got our session. Fantastic. Next, we need our input. Okay. So just like before, so there's a lot of similarities you can see like between these two BERT models. It's just, there's a little bit of differences so far. Like we just don't need this one. Here we go. So we're creating our input now of our input IDs. We have our attention mask, and we've created our lists of lists of lists. So we have these are our tensors, and then we're creating our named ONNX value, which is what, again, our inference session is expecting here. Cool. Okay, so then once we have the input, this is actually going to then run our model, which we don't need to change anything there. There are some, I think, like run options that like some can be useful. If I have 12 on that, I believe it'll show me some of the overloads of different things. So like there's different session options. Let's see if I can. Yeah, so in here, sometimes there's different things that you need to configure about your ONNX Runtime inference session. So there's different graph optimizations. So you can see that they're defaulted, so you don't have to send these in. But if you want to configure specific things for your scenario, you can do that. And this is available in all of the ONNX Runtime packages, whether you're using JavaScript or C# or C++. Or Python. Yeah. So you can look through these and see what you might need, a different optimizations, different execution providers, execution modes. Let's see, what else do we have? All kinds of good stuff here. And I think you can find a lot more about that in the documentation. All right, but, oh, did we look at the other run? I think there's more than just... Yeah. I need to get rid of that. Any questions here? No questions yet. Okay. We will keep going. So we looked at session options. Thought there was, maybe that's the main one. Maybe with the configuration, it's kind of basically just through the session options that you would do that. There's some others in here too. Okay. Let's go back. All right, so now we have our inference session ready, and now we need to get the outputs. Okay, so this output, it's only going to have one value. So let's see, what was this one output called was output logits. All right, so if I go to, I guess this doesn't have to be the same, but it's helpful for someone if they come in here and they're trying to figure out this model and what you did. And if you're like going back and forth between the Python, I try to just name things. For the labels, you need to name, for like using the ONNX model, you need the labels to be the same, but obviously this doesn't need to be exactly the same. And then we want to console.write line. I always think log because JavaScript. And then, well, let's take a look, I think, first about what our input, we might be ready to run this and just see if everything works. We probably should do a sanity run and see if everything's working. But yeah, actually, well, we can print this out. Oh, they could have just hit tab. All right. So in theory, we should be able to run this now, and we would get back, or we would be able to run it now on this model, assuming I got the shape right and everything. And yeah, actually, let's set a breakpoint and step through this so we can see it working. Okay, or not working, whatever happens. All right, so we're creating our tokenizer. You can see our tokenized sentence. We can see our IDs. Oh, and then I don't know if you remember me mentioning about the beginning and end, the separator and the starting index, like, you know, how we skipped that. That's those, you can see that in the tokens, those values that were added. We're going to encode the input. Let's take a look. Does this look right? Attention mask, attention IDs. That all looks good. And if I pull over my console over here, we can, I'm printing out these values as we go. So we can see how it's turning from words into tokens and then encoded for inferencing. Loading our model, creating our tensor. All looks good. Our input. And our input mask. Are those IDs right? Input IDs and input mask. Yeah, okay. Cool. Creating our session and our inference. So we do have, so it was able to inference. And what was that? Let's see, output. Okay. So now we need to figure out how to how to turn this back into a result. So that's where the post-processing code that I don't think I saw in that example. I think we need to go find post-processing, but we were able to really quickly and easily just take another model, change our input shape, use the same tokenizer because it should have been the same base model and run inference, but we need to figure out how to post-process. Okay, so post-process. And I'm going to see if I can find some for this because I've never used this model. That's not the right name of the model. Hang on a sec. This is the, oh wait, this is says for sequence classification. I thought we were doing text classification. Oh wait, that might be the same thing. Let's take a look at this model again. Didn't I pull it up? Where is it? Okay. Let's take a look for comparison. Oh, so if we compute this, what does it give us here? Oh, positive and negative. Okay, so those are our labels. And I would assume that, so we just need to process the two values we got back are the positive and negative sentiment of that. Okay, so it is a classification model. Great. Fantastic. Okay, so now we're getting back these two values and we need to change them into this, which I don't actually think, I think we just might need to do argmax. And I believe that if this first index, I want to find a little bit more documentation first, but I believe the first index would probably be positive and the second one would be negative. And so if we were to go back here, take a look at this. I mean, obviously this is a positive sentence. So ideally, if it is first index is positive, second is negative, well, we haven't argmaxed that yet. So let's see. Let's see if we can find, oh, model documentation. That Hugging Face is just amazing. Like, yes, I do need model documentation. Thank you for having that available. Okay. So we have our input IDs. Although if our tokenization is, okay, so 1 indicates not mask, 0 indicates mask. Assuming our tokenization is correct, that's another thing that I would like to confirm that I'm using the right tokenizer. So I wonder, so one of the things that I was doing too when I was messing around here, so I have Copilot. So I was playing around with like writing, see, so we have text classification from tree chained. Okay, we need the tokenizer still. And let's see if it'll get the tokenizer. Get model tokenizer transformer. See if it'll do it. Oops, with all of my, it did. Oh, Copilot. Okay. Now, let's see. So once we have the tokenizer, okay, we need the same sentence. So our sentence would be, let's just run this quick, make sure that works. Okay. So the way that I do this when I'm trying to figure out how to do it in C# is I'll do it in Python. Like I was showing you before, I'll do it in Python first and I'll mess around with it. And then I can confirm what I'm doing in C# is correct. So we have the tokenizer. I'll create the same sentence. See, I said I'm a person. They said I'm a sentence. Me and Copilot, we're thinking similar, aren't we? Okay, but I'm going to do I like the pizza. You know, that one might be better than machine learning's better than pizza. Okay, so we have our sentence. And then can we say tokenize sentence? And then I was going to say print tokens. That's what I was going to say. Can you get, okay. Let's see. All right, so now we have our tokens, which is good. But so we could go this way, and then we also could, though, because I know I have this code up somewhere here. I thought that our tokenizer, that is not what I wanted to do. I thought our tokenizer was in here too, like our tokenization. Let's see. Transformers, auto tokenizer from pre-trained, pre-hugging face tokenizer. Let's see. So this is doing that different. Let's try this. Wait, no, we don't need to do that. Just kidding. Because this is for their process of the ONNX Runtime extensions. So we don't want to do that. Okay. Let's go back here. I'm going to find an example, like a straight up Python example for this model. Let's see. Still BERT uncased. So this is the base one that it's based off of, which actually this might answer our tokenizer question. I still don't see the inference code. Here's it in Optimum. I want to see what this is. So I don't know if you guys have seen Optimum, but Optimum is one of a project that Hugging Face just released. We actually did a Twitter space about it, and it implements all kinds of, well, here, I'll show it up. All kinds of optimizations that you need to do for machine learning. It's really quite cool. Let's go take. So it helps integrate with different hardware. So like in it actually uses ONNX Runtime on the back end. So it has different accelerators that you can use. And it also has accelerators for training as well. So this is a really neat new, it's obviously all I think transformer based as well. Transformer models, not Transformers like the movie. Okay, but let's go back here and see. So this is around training though. I want to see the inference. Well, we might just have to do it ourselves, I guess. So let's see. This is neat though. This is a neat project. All right, well, let's go back to our Python code because I am not finding any examples. So how do we need to encode. Okay, so we tokenized encode. Yes, that is what I wanted. All right, there we go. So this would be the encoded version of the sentence. Cool. And then let's see. Actually, I wonder if we can reuse some of this down here. We already have our tokenizer. We need a session. Let's see. Pre-process. What's our pre-process? That's what we want to look at. So encoded, convert to tokens. Actually, yeah, I guess that's all we really needed to do there. And then we need to load the model. And actually, I think we could just reuse this because we want to reload that and create our inference session. So let's go back up here. So well, we already have a model. Didn't we already have our model name defined up here, right? Yeah. Okay. So we have model name. We actually have model path. We actually have all of this. We're good here. We also have our tokenizer. I guess all we need to do is create the session. We didn't need all that. But we do need to see model path, inference session. Well, we already have ONNX Runtime imported, so we're fine there. This is just, there we go. Let's call this, because we already have session down there, even though I think we're done running that code. Let's just call this text classification session. Or let's call it text session because that's a lot. Okay. So we're creating our inference session. It's not finding the file. I did export this, didn't I? Let's see here. Oh no, I renamed it. So I got to rerun this 1 second because we need the model re-exported. Or did I not export it? I didn't. No, I thought I did. Wait, hold on. Well, I guess I don't have to export it since we're not. No, where's my export code? Is it down here? That's where it is. Okay, there we go. I think these should probably be 2 separate notebooks because I got a lot going on in this notebook now. Okay, and so now we just need to re-export here. Right, there we go. There's our model. Okay. Now you should find it. Goody. Okay, so we have our model inference session. We have our sentence. We have it tokenized. What do we need to do next? Let's see. So we just need to run inference, right? Oh, we need to create our input. So we're taking in the raw data. Here it's pre-processing it. We've already done that. Then we need to, okay, so is this already separated out into our different inputs that we need? I'm just going to go ahead and grab all of this. Oops, and not cut it. There we go. And we're going to go back up here. I really should have left that up there with the exporting. Why I lost it down here. Okay, so I need my input IDs, which I have here. I also need my mask IDs, which I do not have right now. So what did I miss in the pre-processing? I'm also curious, we should check if this is the same tokenization. See if our tokenizer is right. So run it here. Okay. So I think this is the same tokenizer, but I don't know for sure. So if we look at encoded, it is. Look at that. They all match. So we have 1045, 2066, 3. Yep. Okay. So we know we're getting the correct tokenization. That is very good. And so it means basically all the different like distill BERTs and those type of ones. Just look at whether it's the BERT uncased large or BERT base or whichever tokenizer, whichever the base model was trained from or optimized from, I should say, or fine-tuned, then you can use that same tokenizer. So that means that this tokenizer will support a lot of different BERT models, which is super cool. Such a great open source project. Okay, well, let's go back. We did our sanity check of our tokenization. And then, oh, that's right. Okay, so in here, that's where we left off. We have our encoded tokens, but we don't have our input mask. And I want to look at that down here to see what am I missing with the input mask. So we have tokenizer, convert IDs to tokens. Oh, encoded input IDs. Okay, so this one came back with that. I wonder, is our tokenizer wrong? Well, no, because it's the tokenizer for the model. So why don't we have an attention mask? Let's look back at the model. So this is our model that we're looking at. Okay. Tokenizer. Oh, you know what? I don't know if we grabbed the right tokenizer, but I did have the right result. Hold up. How to get started with this model. Example of single label classification. So we grabbed this value when we called our model, and when we called our tokenizer. However, this is just showing distill base. Okay, let's try this. I want to see if this gives me a different result. Actually, I'm just going to copy this whole thing. And go back over here. This notebook is so long. Okay, let's just throw it at the bottom, right? Let's give us a little space here. Okay, because so this is using distill BERT base uncased. It's kind of hard to say. Still distill BERT base uncased. Got it. And then we were using the fine-tuned version of this. And when I loaded this model, I also loaded. I wonder what the difference is between what the fine-tuned one did. Does it say that in the documentation? Let's see. So it's, oh, from the checkpoint. Okay, got it. And this is the data set it's fine-tuned on, which a lot of times it'll show you with the data set that it used. Is it in here? But anyways, okay, so that was the checkpoint, and this is the fine-tuned version that we grabbed, which is why we have a different one. So I think we did that part right. And then so why in their example are they grabbing the parent model tokenizer? I don't think that should matter unless our inputs don't come back right. Well, let's just try running it and let's see. Let's see if it had a different tokenizer result. Oh, gee, I lost it. Where is it? There it is. Okay, let's try running this. Oh, I should have, Okay, so they had return PyTorch tensors. I wonder if I needed that because if you're using different models, I wonder if I needed that on my tokenizer. Makes sense. Oh, and look, should be trained on a downstream task. So like a lot of these base models, they're made to be trained for a specific answer. So it's a base model that you use. So that's why this is giving that error and why we didn't actually use this one, because we wanted the one that was fine-tuned for the task. But I was curious about this input. I wonder, I'm going to try adding this to our tokenizer and see if that gives me my attention mask. Let's see, tokenizer. That's up there. Wait, what did it be? Okay, so this just has tokenizer. We did tokenizer.encode. Maybe that's it. Maybe we just tokenize. Let's try this and see if that's what we need. There it is. Okay, so that's what we had to do. So now we can actually get the input IDs and the attention mask for our input. Okay, so now that we've done that, we can see. We have our encoded, but we really just want this one. So we want the tokens. And we want to, we can just do it like that because it's a dictionary, right? Let's see. Oh, input ID is not defined. Okay, so what is this? We have, oh, hang on. This needs to be a string, maybe. Still no. Input mask, is it not input mask? Isn't that what it is? Or where is it? Attention mask. Okay, cool. So now if we were to, although was that also, is this already in the right shape? Oh, we don't even have to do that. I think we can just grab this tokens and send it in. We didn't even have to do all that noise, but you know, it was fun, right? Okay. Now we have, so for our output, we actually have a different output for this one. It was just, and what was it called? Sorry, I don't remember. It's in here. Yeah, just output. Okay. We just have the one result here. We have our model inputs, logging. Now we don't have the post process yet. That's what we want to see it in. I'm curious if this gives us the same result as my C# one, and then we can, well, we might not actually have time to post process. We're running out of time here. But that means more fun things for next time. Okay, what requires 3 inputs? Oh, you know what? Is my session my old session? Did I create? Yeah, I need text session because the other one has 3 inputs. This one has 2. There we go. And then I want to print. So input must be at least a list of dictionaries or a single type. Well, I thought they, well, let's see. It's probably gonna be the same thing because they're the same. Oh, I guess we can't. Maybe we did need to do that. Hold on. Maybe we do want to use that model input. Aren't they the same though? Input tensor. Okay, let's go back down. Is this too small? I hope people can see this. Nobody said anything, so I hope that means everyone can see okay. Okay. So, oh, you know what? Oh, wait, that's right. Let's try, I think model inputs a better error. What was that in? So input must be a list of dictionaries or a single NumPy array of inputs. Oh, you can just do the input IDs? Interesting. Can I just do, or do I need to change this to an array, an ND array, or an MP array, I should say. So I'm sending in, oh, it wants a list of dictionaries. So if I do this, does that work? I'll make it a list, maybe. No, almost. Model requires 2 inputs. Input feed contains 1. Okay, so we need to tell it the shape we need because we're going to do 1 batch. So I think, actually, let's see if this will do it for me. Let's see if that will do me so I don't have to look it up. Let's see, run the model. Oh, so that's the other thing with ONNX Runtime. If you don't know the label, you can just write none. Oh, someone did say to maximize. See, I was worried that this was too small. How do I zoom in? I always forget the shortcut because it's not Control Scroll. There we go. So I hope you guys have been able to see this. But okay. No, see, we're still going to have the same problem with this because it's still not the right shape. So Copilot isn't going to do that for me unless I can say create batch for the model. Look at it, even knew what I wanted. God, Copilot's so cool. Actually, that's not, I don't think that's what I wanted. That's not what we want. Wait, maybe it did. Hold up. No, because no, that's just a list. I think that's still wrong. Yeah, we still need, so that solved the, it needs to be a list, but it needs to be a list of batches. So why? This is like really simple and I don't know why I'm thinking it. I think my brain's tired. Maybe that is a sign that we should close up because we are just about out of time here. Okay, good. I'm glad you could see it now. I hope that people were able to follow along on this one. I think the C# one was a bit better, a little bit easier to see. So we went over a lot in this particular example, and I don't have a link yet to share this with you because, like I said, I just wrote the first version of the BERT tokenization one that I showed you, the first project one here this week. So I really need to clean it up so it's ready to be shared. But I'm assuming within the next week or so, I'll have the link available to share this code out. But yeah, we were able to use C# to inference with BERT to do natural language processing. And then we saw how we could take this same example and use it on a different model, which did work right away. It was just the post-processing that we needed to figure out. And so I always kind of go back and forth between how I did it in Python to how I do it in C# to kind of make sure everything is working. So thanks everyone for hanging out with me today. It's super fun. I love when I get to take over the AI show and share this time with you all. So hope you have a wonderful weekend and thanks for hanging out.